Now we'll discuss here the shear stress distribution in the case of symmetrical I section or W section. So we have top flange here and we have bottom flange. In between this we have a web. The top flange and the bottom flange are identical with a width equal to B1, depth equal to D1. And C to D we have a web of depth equal to D2 and the width equal to B2. So A represents here the top fiber and the F represents the bottom fiber of the bottom flange. A represents here the top edge of the top flange. Above this there is no area and below F there is no area, so shear stress at A and F will be 0 because area is 0. So on the top of top edge, that is at point A, we have shear stress tau A is equal to 0. At the bottom of bottom flange, that is at point F, we have shear stress tau F will be equal to 0. Then from A to B, we have depth equal to D1, we have rectangular section. The shear stress will increase parabolically, just similar to the T section. So both this time, because of rectangular area, we have parabolic distribution here, and this value represent here the shear stress at the bottom of the top flange. And this point represents here the point E, which one is top edge of the bottom flange. Both these values are identical. We have symmetrical section here. So the shear stress at B and the shear stress at E are identical value. So in this case, we have shear stress at B is same as the shear stress at E and is equal to the shear force V. This time we have area is B1 multiplied by D1. The distance of y bar from this point will be D by 2 plus D1 by 2. So the y bar will be equal to D1 plus D2 and whole thing is divided by 2. So this one is the centroid G1. This distance is D1 by 2 and this distance from the neutral axis is D2 by 2 divided by the moment of inertia. Moment of inertia is same as B1 multiplied by D1. We have cube of it and the 12 we can shift in numerator. And width at B, that is at the bottom of the flange, is B1 and the top of bottom flange is also equal to B1. So this time it is divided by B1. And what we observed here is that between B and C there is a sudden change in the width. Width has been decreased from B1 to B2 and therefore the only difference is that the shear stress at C and the shear stress at D has the same formula. Instead of B1 you have to take the value of B2. So the shear stress at C and the shear stress at D is given by this formula. Only difference is that you have to take the width of the web. That is at C we have width is equal to B2 as well as D we have width equal to B2. So there is a sudden shoot up here. At the same line we have to show the increased value. So from here we have to mark the value and this value corresponds to the shear stress tau C. Here also from this the same reference level you have to mark the value at shear stress equal to D. Then the area either on the top or bottom is maximum at the neutral axis. So in this case for neutral axis we have tau Na will be same as equal to tau max. And again we have rectangular section, so you have to join this point with a parabola. So this one is the distribution in the case of symmetrical I section or W section. So maximum value always occur at neutral axis. Again we have tau B by tau C. We have a same ratio here. We have tau B by tau C. You have to write this ratio in an inverse proportion. At B we have width equal to B1, so it is inversely proportional, so it is B1. At C we have width is equal to B2. So objective question you can get on the change in the width, sudden change in the width. Now consider here a rhombus whose diagonal is horizontal and vertical and the length of diagonal equal to B. In this case, we will get a maximum shear stress because of a triangular area. The shear stress will not be at a neutral axis. Rather, the shear stress will be at distance equal to 3b divided by 8 from the top edge. And this value represent here the maximum shear stress. Because of symmetry, This distance is also equal to 3b by 8, and the corresponding value will represent here the maximum shear. And at neutral axis here, we have shear stress has been decreased. So this one is representing the shear stress at neutral axis. Shape you have to remember for rectangular section, triangular section, circular section, T section, symmetrical I section. If a beam of a rectangular cross section is subjected to vertical shear force V, the shear stress at the upper 1/3 of the cross section we have to find out, and we have given here 4 choice. So let's consider here we have a rectangle of width equal to B and the depth equal to D. And we can mark here the centroid G and a neutral axis NA. In this case, you have to consider the 1/3 area of the total rectangle, and that is the upper area. So 1/3 area will be equal to is same as equal to 1/3 of B multiplied by D. Now the B is remain constant here. It means that we require the depth that will be equal to D divided by 3. So from the top, we'll take here the height of the rectangle equal to D by 3. So in this case, this area represents here the 1/3 area of the total rectangle. And here you have to calculate the shear stress. So we'll mark this distance here, and let's say this distance is same as equal to Y. So for analysis, I will slightly enlarge this figure. We have depth is same as equal to D by 3. We have width is same as equal to B. So this hatch area of ABCD is area A equal to breadth multiplied by depth divided by 3. You have to look at the centroid of this hatch area, that equal to G1, and you have to measure the distance of G1 from the neutral axis. So as per the CG considered of the hatch area is half of D by 3. So this distance is same as D by 6. This value is same as our Y bar. Since here total height equal to D by 2, you have to subtract D by 3, that you will get the value of Y. So value of Y is same as equal to D by 2 minus D by 3. If you take a LCM here, it will be LCM is 6. So we have 3D minus 2D divided by 6. So we have Y value is same as equal to D by 6. So the centroid location from the neutral axis is Y bar is equal to D by 6 plus D by 6. D divided by 6 plus D divided by 6, that is 2D divided by 6. So we have Y bar is equal to D by 3. So step by step you calculate area, then Y bar width is same as equal to B, and finally use the shear stress formula. So we have tau is equal to the shear force, this time the letter F is used, multiplied by area A multiplied by Y bar divided by the moment of inertia is BD cube by 12 divided by width equal to B. So we have tau is equal to, we have F as it is. Area is equal to BD by 3. So we have B into D divided by 3 multiplied by Y bar. Y bar is same as D by 3. So numerator is complete. Now I is moment of inertia. Moment of inertia is B D cube divided by 12, and width is same as equal to B. So we have 1 by width B. So this B and this B will cancel out. D square, so D cube, so only one D is left. And we have 9 and we have 12. It means that we have 4 by 3. So we have shear stress equal to 4 divided by 3. F. Everything almost get cancelled. In denominator we have B and D. So we have F divided by BD. 4 times F divided by 3 times of BD, our choice B is correct choice. A beam of rectangular section is subjected to transverse load in a section where the shear stress at 1/4 of the beam depth from the top is 120 megapascal. The maximum shear stress in megapascal we have to find out. Maximum shear stress always occur in the case of rectangular section at neutral axis and is 3 by 2 of the tau average. So somehow you have to find out here the value of tau average from the given value of 120 megapascal, which is at a depth equal to 1 by 4 from the top. So let's consider here we have a rectangular beam of width equal to b, depth equal to d. We have a horizontal neutral axis which is passing through the centroid. Dimensions are not given, neither b given, neither d given, but the value of the shear stress at a depth equal to 1 by 4 is given to us. So from the top, if this distance is d by 4, total distance is d by 2, so remaining distance also equal to d by 4. So exactly at this point we have given the shear stress, that is at a distance equal to y, which one is same as equal to d by 4, we have given the shear stress. So we'll hatch this area first, and for this area we'll locate the centroid and the distance of y bar. Figure we have width is equal to b. The given hatch area has a depth equal to d by 4, and by symmetry we can locate the centroid here, and the given fiber here at a distance equal to y, where y is equal to d by 4. So at this condition here we have shear stress tau y is given, that equal to 120 megapascal. This value of the shear stress is same as equal to the shear force V multiplied by area A multiplied by y bar divided by I divided by B. So B is for the given section is known to us, area we have to first find out. So in this case we have area will be same as equal to B multiplied by D divided by 4. One by one term we'll find out here. Let's mark here the centroid here. Then this distance will be same as equal to d by 8. So this distance is d by 8. And if we measure the distance of G from the neutral axis, we will get the centroid distance that equal to y bar. So this distance is same as equal to y bar. Y bar is d by 4 plus d by 8. So we have y bar is equal to d by 4 plus we have d by 8. If you take the LCM, it will be equal to 8. So we have 2 times of d plus d. That is we have y bar will be equal to 3 times of d divided by 8. So that is the sufficient information for us. Using this we try to calculate the average value of shear stress. So we have tau y is equal to 120 megapascal. Let's substitute here. We have V, area is same as B multiplied by D divided by 4. Then we have to write down the value of y bar. Y bar is same as equal to 3 times of D divided by 8. Then we have I in denominator, so we have BD cube divided by 12. So 12 will shift in numerator. Further it is divided by 1 by B. So number of terms will be get cancelled here. So we have 3 into 12, that will be equal to 36. 4 into 8, that equal to 32. So we have 36 by 32. We have shear force is V. This value of B will cancel out this value of B. We have D and D is D square. So one value of D is left in the denominator. That is total value left in the denominator is BD. So V by BD is nothing but our average shear stress is same as equal to 120. So we have tau average is equal to V divided by BD is equal to 120 multiplied by 32 divided by 36. So that value is close to 106.67 megapascal. We are interested in the maximum shear, and the maximum shear in the rectangular section will be same as at a neutral axis. So shear stress at a neutral axis is same as the maximum shear and is equal to 3 by 2 of tau average. That is we have 3 by 2. Tau average this time is 106.67. So maximum shear in this case will come out to be 160 megapascal. In a rectangular beam of width equal to 100 mm is subjected to maximum shear force of 60 kN. The corresponding maximum shear stress in the cross section is 4 megapascal. In the case of rectangular cross section, the shear stress at neutral axis is same as the maximum shear and is given as 4 megapascal. The depth of the beam we have to find out. For this rectangular section, we have width B is equal to 100 mm. Depth we have to find out. At neutral axis we have shear stress is maximum, and this value of tau max is given as 4 megapascal. For rectangular section we have maximum shear that is tau max is equal to 3 by 2 of average shear stress, that is tau average. And tau average is same as the shear force divided by area. So we have tau max equal to 3 by 2. Shear force is V, area is equal to BD. Maximum shear stress at neutral axis is given as 4 equal to 3 by 2. Shear force V is given as 60 kilonewton, is 60 into 10 to the power 3. Width is also given, that equal to 100. Depth we have to find out. The depth D here will be equal to 225, that will be mm. A cantilever member 40 mm long having a rectangular cross section of 20 mm by 100 mm support a load of 6000 Newton. What is the maximum shear stress and where does it occur? So since here we have a cantilever given and one point load is given, the shear force is remain constant because in the shear force diagram you will get here a rectangle. So this one is the right hand side, so you have to show the downward force as a upward force. Shear force is remain constant equal to 6000 Newton, and finally we have reaction is upward, that will be negative value. So this one is the shear force diagram. At any location x, the shear force is remain constant. And we are interested to know the maximum shear. Maximum shear always occur at neutral axis, and this value is equal to 3 by 2 of average shear stress. Average shear stress is same as V divided by B D. Here shear force is constant equal to 6000. So we have 3 by 2. Shear force equal to 6000. Cross sectional area is B by D is equal to 20 by 100. Solve this, you will get a maximum shear equal to 4.5 megapascal. So magnitude wise the shear stress is a very small value. A timber beam of a circular section is to be designed to carry a shear force of 10 kilonewton. Value of V is given equal to 10 kilonewton. The allowable shear stress is 5 megapascal. Safe minimum diameter of the section we have to find out. We know that in the case of circular section, the maximum shear stress will occur at a neutral axis and its maximum value is equal to 4 by 3 of average shear stress. And the average shear stress is given as V by A. The tau allowable will be equal to 5 megapascal. So this value of tau max should be less than equal to tau allowable, which is same as 4 by 3 of average shear, and we have average shear is V by A, and we have area equal to pi by 4. So we have pi, 4 will shift in numerator divided by d square, must be less than tau allowable. So we have d square should be greater than equal to 4 and 4 is 16. So we have 16 times V divided by 3 divided by pi divided by tau allowable. So we have d square should be greater than equal to 16. Shear force here is equal to 10 kilonewton is 10 into 10 to the power 3 divided by 3 pi, and we have allowable shear stress is equal to 5 megapascal. Solve this and you will find here diameter after taking the under root should be greater than equal to 58.27 mm. The video you are watching is from the app, which is the Mohod class app available on Google Store. And in this app, we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.